All right, hi folks, this is Larry Mussolino. I wanted to record a short video to help you get started in the Module 6 homework in my labs. And so let me do a few examples here, and hopefully this helps you get up and running here in the homework. Let me come here to number 2. It says a rectangle is constructed with its base on the x-axis and two of its vertices on this parabola y equal 4 minus x squared. What are the dimensions of the rectangle, and then what is the maximum area? All right. So let's draw a diagram to get started. I think that's always a good idea with these kinds of questions to visually see what's going on. If you were to graph this y equal 4 minus x squared, it would graph as a parabola opening down. The reason I know it opens down is the number in front of x squared here is negative. So if the number in front of x squared is negative, that tells you the parabola opens down. So this graph is going to do something like this. By the way, the y-intercept is when x equals 0. And so if x equals 0, let's let x equal 0. Then y equals 4 minus 0 squared, which is just 4. So 0, comma 4 is on the graph. That's this point right here. 0, comma 4. And so this graph looks something like this. All right. And so the base of this rectangle is on the x-axis. So let me draw it here. And the height is, let me undo that because I think I drew that not correctly. Let me put two vertices on the parabola. So they're telling me that one corner is here, another corner is here. And so let me draw the rectangle looking like this. So here is our rectangle. All right, let's call the height of the rectangle y. And each one of these bases going this way, I'm going to call x, and x going this way. So really this base is going to be 2x. All right, they're asking us to maximize area. So let's write the area of this rectangle. The base is 2x, the height is y, so 2xy. Now what we're going to do here is to find the max, we're going to take the derivative and set it equal to 0. For the derivative, I'll just write that as a prime. We'll set it equal to 0. The reason you do this is when a graph hits a maximum, so we're going to be plotting area here versus x. When a graph hits a maximum, the tangent line is a horizontal line. So the slope of the horizontal line is 0. But the slope is really equivalent to the derivative. So when you hit a maximum, because the slope of the tangent line is 0, it makes sense to set the derivative equal to 0. All right, but in this area formula, I don't want there to be an x and a y, because now to take the derivative, I would have to use the messy product rule, and I'd like to avoid that. Well, we can make this area function have just one variable by getting rid of this y. Because remember, we have the equation y equal 4 minus x squared. So let me replace this y here with, I'm going to replace this y with 4 minus x squared. All right, let me multiply this out. This is going to be 8x minus 2x to the 3. So here's the area. But we want to take the derivative and set it equal to 0. So let's take the derivative. I'll just call it a prime. I could call it dA dx. All right, well, this is going to be 8 minus 6x squared. By the way, I'm using the rule. This is called the power rule for derivatives. It says if you have a function which is x to an exponent, x to the n, its derivative is n times x to the n minus 1. So what you do is you take this exponent n, bring it down in front as a multiplier. The new exponent is 1 less than what you started with. All right, we want to set this equal to 0. Let me add 6x squared to both sides. Divide both sides by 6. So x squared is 8 over 6, but that's 4 over 3. And I'll just take the square root of both sides. So I'm going to take, x is going to be the square root of 4 over 3. Normally, I would put a plus or minus. but I'm just going to use the plus answer because I know it'll be an x going that way and an x going this way. All right, if I work that out on my calculator, square root of 4 over 3, I'm getting the answer 1.1547. So x equals 1.1547. Well, now I can figure out this base because the base is 2x. So the base of this rectangle is going to be 2 times 1.1547, which works out to be 2.31. We're rounding to 2 decimal places here. So for this rectangle, let me erase some of this stuff here. For this rectangle, we're finding out that this x dimension is 2.31. Well, what about the height? Well, that's the y value, but the y value is 4 minus x squared. So 4 minus 1.1547 squared. If you work that on your calculator, you get 2.67. So this height is 2.67. Now to find the area, I can just multiply these two numbers together. So the area of this rectangle is just 2.67 times 2.31, and that's how you come up with this 6.16. Okay, so we wrote an equation for the area of the rectangle. We ended up getting this area equation to use just one variable, x. Take the derivative, set it equal to 0. All right, let's look at another example here. How about if we go to, I think there was another question on derivatives, number 5 here. All right, let's take a look at this one. So this one is asking you, looking at these 3 graphs, which one of these graphs meets the criteria shown in this table? All right. Well, they're asking us for a derivative. They're showing derivatives in this table. So let me recreate this table here so we can discuss it. So point A, B, C. And notice A, B, and C are labeled on this x-axis for us. All right. What if the derivative is 0? Well, remember, derivative means slope of a tangent line. So they're telling us the slope of the tangent line is 0. But a 0 slope means a horizontal line. So if this is the slope of the horizontal line, it means we've reached a maximum or minimum on the graph. So at point A, I'm looking for either a maximum or a minimum. All right, what about point B? Point B says does not exist. When does the derivative not exist? Well, if you end up with a V-shaped graph, or what's called a cusp. So if you have a graph that does something like this, at this point, the derivative does not exist. Or if you have something like a corner where the graph does something like that. So at point B, we're looking for a corner, not a smooth curve, but a corner. I'm looking at graph A. Here at B, it's a smooth graph here. So this answer A must be wrong. All right, here at graph B, there's a sharp corner. It's hard to see this, but if you zoom in, you can use these buttons, by the way, to zoom in. This looks like a sharp corner. So this graph is okay right now. Here, this graph has a sharp corner. So this graph is okay. This graph looks like a smooth curve here at B, so this must be wrong. So we've eliminated choices A and D. Let me go to point C. It says the slope is -1. Well, that means the slope of the tangent line is -1. Well, for a slope to be a negative, think about a graph. Here's a graph. Let me think about the slope of the tangent line over here. Well, this tangent line would be going uphill. This slope is positive. Over on this side, this slope of this tangent line is negative. Our slope is -1. That must mean our graph is decreasing at point C. Well, if I come over here to this graph, I'm noticing here this graph is increasing at point C. So this graph must be wrong. If you notice here, this graph at point C is a decreasing part of the curve, which makes sense. So I think our answer here is answer C. Just to summarize, at point A, you should be reaching a max or a min. Yes, here it is. We reached the min. At point B, you should have a V shape or a cusp. Yep, here's a sharp corner. At point C, you should have a decreasing, a downhill graph. Yes, we do. So graph C meets all three of these conditions. Okay, so really no calculations needed on this one. We just had to analyze the derivative for each of points A, B, and C to come to a conclusion on this one. All right, let's do one or two more. How about, let's take a look here at number 9. This is referencing something called the mean value theorem. And what it says is if you have a continuous function, then this equation must be true. So C is some x value in the interval AB. And so what it's saying is if you had a graph, let's say that does something like this, and you think about this slope calculation, let's make this A and this B. The slope calculation is really giving you the slope of the line connecting these 2 points. So this part of the equation is the slope of the line. What it's telling you is at some point on this curve, the slope of the tangent line must equal that same slope of the red line. So let me just make up a point. Let's call this point C here. There must be a point here where the slope of the green line is exactly the same as the slope of the red line. So there has to be a point C where these two lines are parallel. That's what this theorem is telling you. All right, well, let's do this. Why don't we take the derivative of this function? If I take the derivative, it's going to be 6x minus 5. All right, and let's work out f prime of c. So what I want to do is I want to set up an equation according to this equation they gave us. So let's work out f prime of c. Well, f prime, remember, c is unknown. We got to figure that out. F prime of c is just 6c minus 5. So this is 6c minus 5. All right, let's work out the left side of this equation. Maybe I'll do it over here. Let me erase some of this for a little more room. So let's work out this f of b minus f of a over b minus a. Okay, in our example, the a value is -3, the b value is -1. So let me work out f of -1 over, maybe I'll do it over here on the side, f of -1. That's 3 times -1 squared minus 5 times -1, subtract 2. That is 3 plus 5 minus 2. That is 8 minus 2. That's 6. So this answer is a 6. All right, let me work out f of a. That's going to be f of -3. That's 3 times -3 squared minus 5 times -3 minus 2. Let's see, -3 squared is 9. 9 times 3 is 27, plus 15 minus 2. I think that's 42 minus 2, which is 40. So this answer is a 40. Over b minus a, that's -1 subtract a -3. And we're going to set this equal to f prime of c, which is 6c minus 5. Well, I think you can see this is an equation you can solve for c. Let's do it here quickly. The top is going to be -36. The bottom of this fraction is -1 plus 3. So this is 36 over 2, -36 over 2. And that's equal to 6c minus 5. -36 over 2, that's -18. equals 6c minus 5. I'm going to add 5 to both sides. And let me work this out. Right, I just noticed I have a small mistake here. Let me fix an error on my part here. 6 subtract 40, that should be negative 34, not negative 36. So this is negative 34. Let me erase this stuff here to fix this. So we're really ending up here with a negative 34 over 2, and that's equals 6c minus 5. Well, that's negative 17 equals 6c minus 5. Let me add 5 to both sides here. So we have 6c equals negative 12, so c equals negative 2. So our answer here is c equal negative 2. Okay, so if you were to graph this, let me do a quick graph just to finish this problem up. If I was to graph this, let me just make a little more room here. I don't know exactly what this curve looks like, but let me just simulate. We're going from negative 3 to negative 1. So here's negative 3 to negative 1. And so maybe this graph does something like this. We found the slope of this line to be negative 17, right? When we worked this out, it was negative 17. So the slope of this straight line connecting these 2 points, this slope is negative 17. But what we found is if you go to c equals negative 2 and think about the slope of the tangent line, I'll do that in blue. The slope of the tangent line is also negative 17. Okay? And I think you could see that, by the way. If you take f prime of negative 2 as a double check, it would be 6 times negative 2 minus 5. That's negative 12 minus 5. That's negative 17. So at this c value of negative 2, the slope of the tangent line is equal to the slope of the secant line. Right? The secant line is the straight line joining those 2 points on the curve. All right, let me do one more example, maybe one that's a little different. All right, here's an example that's going to ask you about something called critical points and also ask us about increasing, decreasing intervals. Well, here's what we could do. Let's say we have a graph that does something like this. The first thing I want to know is where are these max mins? Well, at those points, max mins, the tangent line goes horizontal. So the slope here is 0. Well, that's what critical points are. Critical points are x values where the derivative is equal to 0 or where the derivative does not exist. Well, they gave us the derivative function already. They worked it out for us. So we want to take this derivative function and set it equal to 0, because that's going to give us max mins. Well, I'm going to set each one of these parentheses separately equal to 0. So 3x equals 0. That tells me x equals 0. And x plus 2 equals 0. That tells me x equals negative 2. We call these critical points. These are x values where the derivative is 0. All right, we know that part. Here's what else we want to know is where is the graph increasing or decreasing? Well, the way you can do that is select any kind of a test point. Let's say I select a test point back here. If I check the derivative here and the derivative is positive, notice here the derivative is going to be positive, that tells me the graph is increasing. Remember, derivative is equivalent to the slope of the tangent line. How about if I pick a test point here? Well, this slope would be negative. That would tell me the graph is decreasing. So if I can find the derivative for some test points in these intervals, if the derivative is a positive number, the graph must be increasing. If the derivative is a negative number, the graph must be decreasing. All right, here's a good way, I think, to do it is set up a little number line. Let me set up a number line here, and I'm going to mark the critical point. So x equals 0 and x equal -2. Whoops, let me fix this. Let me make this x equal -2. And here is x equals 0. So these are the critical points. I know these are going to be either max mins, but I want to know what happens in between these intervals. So let me pick a test point. Back here, I'm going to pick any value I want for x as long as it's less than -2. So I'm going to pick -3. In the middle here, I'm going to pick any test point between -2 and 0. So I'll pick -1. And over here, I want to pick any test point greater than 0. I'll pick a 1. What I'm going to do now is evaluate the derivative for that test point. If this derivative is a positive number, that tells me the graph is increasing. But if this derivative is a negative number, it tells me the graph is decreasing. All right, let's do it. I want to work out the derivative when x is -3. So I want to work out f prime of -3. So I'm going to be plugging into this derivative formula. So it's going to be 3 times -3, -3 plus 2. Now, I'm not going to bother to work this out because all I really care about is this answer positive or negative. So here's what I could do. I can look at this part and say, well, 3 times -3 is negative. -3 plus 1 is negative. But negative times negative is positive. So we just figured out in this interval here, the derivative is positive. Well, that tells me this interval is increasing. So the graph must do something like this. All right, let me, by the way, let me label these intervals maybe to make it a little easier. I'll call this interval A on the left, interval B in the middle, and interval C on the right. So we just worked out interval A. Let's go to interval B. Our test point here is -1, so I want to work out f prime of -1. All right, 3 times -1, -1 plus 2. Again, let me just do my positive-negative analysis here. 3 times -1 is negative. -1 plus 2 is positive. But negative times positive is negative. So in this middle interval, we just figured out the derivative here is negative. Let me write that better. Derivative is negative. But that tells me the graph is decreasing in this interval. So I'm thinking the graph does something like this. All right, one more interval. Let's do interval C. For that, I want to work out f prime of 1. That's going to be 3 times 1, 1 plus 2. Well, this part is positive. This part is positive. Positive times positive is positive. So that means this graph, the graph is increasing on that interval. So increasing on this interval. So the graph turns and goes uphill like that. All right, let's answer the question. Where is the function increasing? Well, that's what we called interval A and C. Interval A is -∞ to -2. Interval B is 0 to infinity. Where is the graph decreasing? That was our middle interval. I'm sorry, I should have said interval A and C here. Where's the graph decreasing? That's our middle interval. That's what we called interval B, from -2 to 0. By the way, in these intervals, don't use the test points. The test points are just random numbers you're picking. The intervals have to make use of these critical numbers that you labeled on the number line. All right, the last part to this question was, where is there a maximum or minimum? Well, if you notice, by my sketch, right, if I draw this increasing graph here, the decreasing part here, the increasing part here, now I visually can see this point right here must be a maximum. It's like the top of the roller coaster. So I'm seeing there's a maximum at x equal -2. When I look at my graph right here is a min, right? It's like the bottom of the roller coaster. So my conclusion is there's a minimum at x equals 0. So I think creating a number line like this is a big help because you visually see where the graph is increasing, decreasing. All right, folks, hope this is helpful as you're getting started in this Module 6 homework.